We want to keep moving forward with quantum numbers and talk about how they define orbitals and, finally, electrons. So our third quantum number is called the magnetic quantum number, and our symbol for this is an M with a subscript of the swoopy L. And so we call this M sub L. That's kind of the lingo and how I'm going to talk about it. M subscript L, just kind of shorten it, M sub L. And so this quantum number similarly characterizes an organizational unit of where you can find electrons, and we finally have reached the orbital level. So M sub L indicates the orbital of the electron. So this really does indicate where kind of the final level of the orbital, sorry, of the electron, where it's located. And so this serves as an index of each orbital. And so the values for M sub L depend on the subshell. So just like we saw previously that L values depended on N, whatever the N value is, here the possible values for M sub L depend on the L value. So kind of the wording would be that the number of orbitals varies depending on the subshell. So different subshells have different numbers of orbitals. And so our kind of our numerical relationship is that there are two L plus 1 orbitals in subshell L. So whatever the value of L is determines the number of orbitals in that subshell. And so kind of the relationship of the particular values of M sub L then as we go from negative L, we count up by 1, include 0, count up by 1 again until we hit L. Okay, so for example, L equals 2. We would call that a D-type subshell, right? So if L equals 2, then the lowest possible value is negative 2, and the highest possible value is 2. And you just count up by 1. So negative 1, 0, and then 1. So go boop, 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 1 at a time. And so that's kind of the overall track that we would see. And so the reason why it's 2 times L plus 1 is basically, if you think in this case, L was 2, so you have the 2 from the positive and the 2 from the negative, so it's the 2 times L. And then the plus 1 is 0. So there are 5 possible values of M sub L when L equals 2. We can count them out, what they are. And so that's just kind of this numerical relationship. So what's going on for the kind of organization of electrons is we would say that L equals 2 means this is a D subshell. And this relationship tells us that there are 5 orbitals in a D subshell. And you'll note we have not made any mention to our N quantum number. So this is true of all D subshells. All D subshells contain 5 different orbitals. So if you have a 3D, a 4D subshell, 5D subshell, doesn't matter what it is, what the shell is, there are 5 orbitals within that subshell.
All right, so now that we've finally got some orbitals, now that we have our kind of arrangement, we can go all the way down to orbitals. What we want to do is we want to look at what these actually look like. And so our orbitals have characteristic shapes that are based on the L quantum number. So S orbitals are spheres. P orbitals are dumbbells. D orbitals have a clover shape, and F orbitals are called a double clover. Okay. And so how we can think about this is one, as we see SPDF, we know that's the L quantum number increasing. And we can see that unsurprisingly, the shapes get more complicated. So as you get to these higher order subshells, SPDF, we can see that the shapes become more complicated. And what really is going on is basically you can imagine if you took a sphere and you kind of pinched it across, that'd be the same as this line that you cut in through the P dumbbell. Similarly, if you took the P and you cut it across that direction, that would be this cut, that pinch that you have across. And then you can pinch one more time to get to the double clover for F. You pinch in the plane of the screen. Okay, so once you determine your L quantum number, right, that angular momentum quantum number, you determine the shape of the orbitals. So L equals 0 is S type. We can see the spheres at the top. Then we have the L equals 1, L equals 2, and L equals 3. And one of the things we can see is that they all have the same shape within a row, or similar shapes within a row, And then the different values of m sub L, which are the different orbitals, have different orientations. So you only have one orientation for the sphere. You have 3 orientations for the dumbbell, basically front, back, and side to side, right? Up, down, left, right, and front, back. Those are the possible orientations. And so then for L equals 2, you have 5, and for L equals 3, you have 7. And so we can see that as you get more complicated shapes, there are more and more ways to arrange those shapes. But those are just the different m sub L's. They still all have the same shape. And so we can see again that there are 2 L plus 1 orbitals in the L subshell, right? This was 0 to 1. 2 times 0 is 0 plus 1 is 1. 2 times 1 is 2 plus 1 gives you the 3. 2 times 2 is 4 plus 1 gives you 5. 2 times 3 is 6 plus 1 gives you 7. So we can see these relationships that build up. These different orbitals are just different orientations of the same shape. You'll note at the bottom some of the shapes get a little wonky, but they're still the same idea. You also notice the same number of colors. All right, so we know that if we're looking at an orbital, we can start to see there's some properties that are cooked in with the quantum numbers. We had shape and orientation. Principal quantum number then determines the size of an orbital. So again, s orbitals, always spheres. It doesn't matter which s orbital you're looking at, 1s, 2s, 3s, 4s, 5s, 80s, a million s. You're always going to be spheres. The only difference is the size. And larger values of n just have larger orbitals. So that makes sense. The bigger the shell, the bigger the orbitals, right? The higher the shell, just literally the further away the orbitals are from the nucleus. All right, so we have these quantum numbers, and we know that they really are they're in that equation, they're underlying the mathematics of what the orbital looks like. But they also, the reason why we use them is they give us a complete description of the electron that we're talking about, the orbital that we're talking about. So there's kind of these 2 designations. First is the address. That's like an organization. Where is the electron? Kind of how can we find it? N corresponds to shell, L corresponds to subshell, and M sub L corresponds to orbital. You know, kind of like state, city, street, if you will, right? Like kind of that narrowing organization of where is this electron? If the atom is the country, right, then shell is like the state, subshell is your city, and orbital would be like your street or zip code or something like that. So orbital description then is what information about the orbital is cooked in to from the quantum number. And this is how it shows what they are actually doing in the equation that we have. And n corresponds to the size of the orbital, with larger n's having bigger size. L corresponds to shape. You have those SPDF, sphere, dumbbell, clover, and double clover. They get more complicated in shapes as L increases. And then you have orientation. That's just kind of spinning around the different directions. But you have those different orientations. But importantly, when you get, say, P, they're all going to be the same shape. The different P orbitals within a given subshell just point in different directions. So what we can do is we can put all of this together in terms of kind of counting and figuring out what all these orbitals are from these quantum numbers. So I have a value of n. First possible value is 1. I can only have L equals 0, so I have a 1s subshell. M sub L can only be 0, so I have 1s orbital, right? Because those are the possible values for the quantum numbers. When n equals 2, L can be either 0 or 1, so we have a 2s and a 2p subshell. Inside that 2s subshell, there's only one possible value for M sub L, so there's one 2s orbital. That's going to be true for any s-type subshell that you have. You're always going to have that relationship. When you have the 2p, though, now there are 3 possible values for M sub L, so there are 3 2p orbitals in the 2p subshell. N equals 3, L can be 0, 1, or 2. When L equals 0, we get 3s. Just like the other s's, there's only one orbital in that subshell because M sub L only has one possible value. For the 3p subshell, just like we saw for 2p, you can have -1, 0, or +1. There are 3 3p orbitals. That's always true of p's. And then when we get to L equals 2, then we now have 5 possible values for M sub L. So there are 5 3d orbitals. If we go to n equals 4, we now have 4 possible values, 0, 1, 2, 3. the 4s, 4p, 4d, 4f. S, just like we saw previously, the same restrictions because it's all just based off the letter now. We get 1 4s orbital, 3 4p orbitals, 5 4d orbitals, and then 7 4f orbitals. So one of the things you can see is this is going up by odd numbers, 1, 3, 5, 7. The next one is 9, then 11, then 13. All right, the final quantum number is the electron spin quantum number, which is called m sub s. This represents the 2 possible spins of an electron. So there are 2 possible values of m sub s, -1/2 and +1/2. Okay, so electrons, this property is called spin. The electrons do not actually spin. They instead respond to magnetic fields as if they're spinning charges. So people initially thought they were spinning, and we just kept that word. This is a purely like quantum mechanics, weird business going on with electrons property. But this actually is where magnetism comes from, is that electrons have this inherent property of spin either up or down. So you can see they either spin up, that'd be +1/2, or down, which is -1/2. One of the things, this is a purely electron property. You'll note that this does not, there's no relationship to N or L or M sub L, nothing like that. They're just in there.
Participation 622, question 1. For each of the following statements, provide the word that correctly fills in the blank. 1, the principal quantum number n describes the blank of the orbital that the electron is located in. 2, the angular momentum quantum number L indicates the blank that the electron is located in. 3, the magnetic quantum number m sub L indicates the blank of the orbital that the electron is located in. And 4, there are only blank possible values for the electron spin quantum number m sub s. First question on participation 622, due Monday, June 22nd at 11:59 p.m. over on Blackboard. Link to the assignment is right below the links to these videos. Again, for each of the following statements, provide the word that correctly fills in the blanks. 1, the principal quantum number n describes the blank of the orbital the electron is located in. Angular momentum quantum number L indicates the blank that the electron is located in. The magnetic quantum number m sub L indicates the blank of the orbital that the electron is located in. And there are only blank possible values for the electron spin quantum number m sub s. First question on participation 622. I'm sure there will be more. See you in the next video.